So let us start with the derivation of the energy equation, and the derivation of the energy equation will be very similar to how we have derived the momentum conservation equation and the mass conservation equation. We take a control volume and we write down we give a statement of the energy equation for it, and then we evaluate each of the terms, noting that the energy that we are dealing with can be changed. The energy content in a control volume can be changed by the addition of heat into the control volume externally, by the work done on the fluid which is contained in the control volume by external forces, and it can also result from the advection of energy because it is part of the along with the flow, and any other source terms that may be there that can come into picture. So what we do is that we take a control volume like what we have done earlier, and as usual we locate the origin at this point. This is our x direction, y direction and z direction. The control volume has delta x width in this direction, a height of delta y in this direction, and a depth or the length of delta z in this direction, and this is a cubical control volume. And we can say that the rate of change of energy in the control volume is equal to rate of inflow of energy so when there is inflow then the energy increases minus rate of outflow of energy plus rate of heat addition to the fluid contained in the control volume. We are distinguishing heat as a specific form of energy plus the rate of work done by the forces acting on the control volume. These are external forces, and we have made the point that there are stresses, viscous stresses, and also the pressure forces which may be acting, and when you have a force acting on a particular control volume then it can do work and that becomes part of the external work, and if there is external work done on the system, on the fluid within the control volume, then its energy content increases. So that is why we have plus rate of work done plus volumetric plus generation of energy from sources within the control volume. Okay, so this gives us a balance, a statement of the balance of the energy that is contained within the control volume, or energy possessed by the fluid which is contained within the control volume. Now first of all we have to clarify what we mean by energy here. What energy are we talking about? We are talking about energy as that associated with the what is known as the internal energy which is CV times T minus T reference. So, this is the energy associated with the fluid having a temperature T, where CV here is the specific heat at constant volume, plus kinetic energy and this is associated with the velocity half rho v square, and in the specific case where we have 3 velocity components, this becomes half of rho times u square plus v square plus w square, where u, v, w are the 3 components of velocity. So, we have potential energy also is that is considered as a form of energy, but we will see that when we consider gravitational force as an external force which is acting on this, then the gravitational potential energy associated with the gravitational field will come in through this particular term, rate of work done by the forces acting on the control volume, so that we do not have to include that in this. So, we are looking at the rate of change of energy, rate of change of internal energy and kinetic energy possessed by the fluid within the control volume, which is attributable to rate of inflow of energy, because this control volume is actually a small part of the fluid expanse and fluid will be flowing through, and as it flows through it brings in whatever property it has, and therefore the fluid coming in with the property of internal energy which is associated with the temperature and the velocity, it also brings in energy, and similarly any fluid that is going out of the flow domain will also carry away with it the energy, internal energy associated with its temperature at the outlet point and the velocity at the outlet point. So, these are the 2 terms that are coming here, and heat addition from outside is something that we are considering specially, and we already have acknowledged the fact that there are forces acting on it and the rate of work done by the forces that are coming here. Now, this generation of energy is a special case, and if there is a generation, for example due to a nuclear reaction which may be happening inside, or due to a chemical reaction which may be happening within that, we can definitely consider that. So, we will not expand on what specifically the generation, how the generation of energy is taking place, but what we have in mind here are the generation from factors which are distributed entirely within the control volume. So, we are not looking at a generation at a particular point within the overall flow domain, but something that is distributed throughout. So, the most appropriate thing probably would be a nuclear reaction or a chemical reaction which may be happening within that. So, we will just put this term as some S phi S the ST here with the subscript capital T indicates that this is a thermal energy source term. We will leave it at that particular thing, and we will try to evaluate each of these in terms of the properties that we know, so that we can write down the overall energy balance equation. So, let us write an expression for this. We know that we are talking about internal energy and kinetic energy, and we write down the specific energy part of it, that is the energy per unit mass. So, we can call this particular internal energy as equivalent of small e. Okay. So, small e is such that capital E, which is the total internal energy, is m times E, where m is the total mass which is contained within this. So that is rho times delta x, delta y, delta z times E. So this gives us the total internal energy, and similarly the total, we will put this as T there, and total kinetic energy I am putting roughly as this, is half m v square. So that is v dotted with v. So again this can be written as half rho delta x, delta y, delta z times v dotted with v. So we can write therefore that the rate of change of time rate of change of energy within the control volume can be written as partial with respect to time, indicating the time rate of change of energy as rho delta x, delta y, delta z of E plus half u square plus v square plus w square So that is the rate of change of energy that is in this is equal to rate of inflow of energy, and inflow is always inflow of something is equal to the mass flow rate times the specific quantity there. Okay, so we can write that as, we know that the mass flow rate, if we were to put like A, B, C, D and E, F, G, H as the vertices, visually we can see that this is an inflow surface, that is the negative x phase, and similarly the bottom face is an inflow phase, and then the back face is an inflow phase for this, and the flow rate through each of these is rho times the cross sectional area, which in this particular case is delta z times delta y, times the normal velocity at the centroid. So we can write that as rho delta x, delta y, delta z times u at x star at x, y star, z star, where the star quantity indicates the central point of y and z for that particular phase. So this is the flow rate times the specific energy that they are bringing in is E plus half rho v dot v. Okay, so this is what is coming in through the x phase, and through the bottom phase. So this is what is coming through the left phase. So we can write this whole thing as at x, y star, z star, and we can consider immediately also what is leaving through the positive x phase, that is the right phase. So we can write that as minus, since it is leaving we put minus, rho times the cross sectional area delta y delta z times u times E plus half rho v dot v at x plus delta z, x, y star, z star. So this is what is going in through the left phase and coming out through the right phase. Similarly, what is going in through the bottom phase, rho times the cross sectional area, which is delta x delta z, times the normal velocity v, times the specific quantity, this whole thing evaluated at x star, y, z star, minus what is leaving through the top face is rho times the cross sectional area times velocity times the specific quantity, whole thing evaluated at x star y plus delta y z star plus, now we consider the back face. The mass flow rate is rho times the cross sectional area, which is delta x delta y, times the normal velocity w times the specific quantity E plus half rho v dot v. This whole thing evaluated at x star y star z minus what is leaving through the front face, which is rho times delta x delta y times w times E plus half rho v dot v, evaluated at x star y star z plus delta z. So these 6 terms represent the rate of inflow minus rate of outflow of energy through the 6 phases of the control volume, plus rate of heat addition. We say that heat is coming in, for example, by conduction through the phases, and at each phase we have a heat flux Q. Q is the heat flux, and this is a vector quantity. So this has 3 components, Qx I plus Qy j plus Qz k. So since flux is a vector quantity, there is a component in the I direction, z direction and k direction. So this heat flux vector has to be dot producted with the area normal vector in order to find out how much heat is coming in through that particular phase. And when we take the dot product, then because we have taken these area phases to coincide with coordinate directions, for an x phase we take the corresponding x phase area, these things will be 0. For a y phase, that is bottom phase or a top phase, we take only the Qy component of this flux vector, heat flux vector, and multiply by the cross sectional area delta x delta z. And for a front phase or the back phase, we take the Qz component of this and then multiply by the corresponding area, which is delta x times delta y. So this, because we have taken the phases to coincide with coordinate directions, the evaluation of this term will be simplified. So by definition, Qx positive means that it is going in the flux is in the x direction. Okay, so we can write at the left face Qx is in the positive x direction, so it is coming in. So Qx times the cross sectional area of this particular phase, which is delta y delta z, evaluated at x y star z star, and at this phase, that is the positive x phase, that is the right phase, Qx is actually leaving. So that means loss, it is not being added, it is being subtracted, the system is losing. So Qx times delta y delta z at x plus delta x y star z star. Similarly, when we consider the bottom phase, it is a Qy component that has to be multiplied by the cross sectional area, and Qy at the bottom phase is in the vertically upward direction. Therefore, whatever heat flux that is there, Qy, positive value of Qy at the bottom phase will be coming in into the control volume. So it is added, cross sectional area is delta x delta z, evaluated at x star y z star. The heat flux through the top phase is something that is leaving, so that is Qy times delta x delta z with the minus sign evaluated at x star y plus delta y z star. Okay, so we have now evaluated 4 of these phases. Similarly, the back face and the front face. At the back face, the non-zero component of the product of the heat flux vector with the surface area vector will be qz times the cross sectional area, which is delta x delta y. This is the heat that is coming in, and this is evaluated at x star y star z minus qz delta x delta y times and this is the heat flux that is leaving through the front face evaluated at x star y star z plus delta z. Okay, now what is left? We have the rate of work done by the forces acting on the control volume, and we have the source term here. So we can first deal with this. So we can, if we declare this as the volumetric source term, so this times delta x delta y delta z is the volumetric source term, and if we call this as per unit mass, then it will be rho times this. Okay, so we will call it as per unit mass. So with that we can deal with this. Now the evaluation of the rate of work done by the forces acting on it is a tedious process, but it is relatively straightforward. We have to identify what the different forces acting on the control volume are, and we know that there are on each face there are pressure forces and there are viscous stresses, and not only that, there is gravitational force, which is the body force that is acting. So let us deal with first of all the gravitational force. The gravitational force has forces are there in each direction. So you have forces in the x direction, y direction, z direction, and if you have force F dotted with displacement ds will give us the work done, okay, and that divided by time is the rate of work done, and we are looking at rate of work done. So this is can be written as F dotted with V, where V is the velocity of the particular fluid component. Okay, so this is what will be given to us. In the case of body forces, then we evaluate the body force. So this will be Fb dotted with V, and in the case of stresses, we have to look at the stress times the area to convert into a force, and that is dotted with V. So we have to consider the various stresses and body forces, and there are 3 components here. Fb will have Fbx, Fby, Fbz dotted with V, that is UVW. So you get U times Fbx plus V times Fby plus W times Fbz. When we consider Fb, the body force, to be coming from the gravitational thing, then we can write it down as rho g x times U plus rho g y times V plus rho g z times W. Okay, so this is and the total volume. So this is the contribution of the gravitational force as the only non-zero body force that we are considering, and gx, gy, gz are the 3 components in the xyz direction, so the gravitational vector. Now what about the stresses? Here we have to look at all the stresses acting in the x direction and y direction and so on. So let us consider, for example, in the x direction, if we take this particular phase, at the centroid we have pressure acting as a compressive force, and we also have the viscous stresses. Viscous stresses, there is a viscous stress tau xx, and we have on this particular case, that is the only stress that is acting in the x direction. At the top here we have tau yx, and at the bottom we have tau yx oriented in this direction, and then we have on this side we have tau xx on the negative phase acting in the negative direction, and the back phase we have tau zx acting in the negative z direction. On the front phase we have tau zx acting in the positive x direction. So each of these stresses has to be multiplied by the appropriate area, and we have to take the corresponding velocity component, and since all of them are acting in the x direction, the velocity component here will be u. Okay. So we take, for example, this P here, pressure force acting on this, and similarly we have pressure force acting on at this space. So if you consider just the x direction forces, and out of that x direction stresses, and out of that the pressure as a stress acting on the x phase, left phase, the contribution is plus P times the area, which is delta y delta z, evaluated at x, y star, z star, and on the right phase it is acting in the opposite direction, in the negative x direction. So that is minus P delta y delta z evaluated at x plus delta x, y star, z star. Now consider the stresses tau xx acting on the x phase, that is acting in the negative x direction. So we can write this as tau minus tau xx delta y delta z at x, y star, z star. On the positive x phase, then that is tau xx delta y delta z at x plus delta x, y star, z star. The negative y phase, that is the bottom phase, that is minus tau yx times the area on which it is acting is delta x times delta z. Oh, we forgot to put the corresponding velocities because it is just the force, and here this is multiplied by u. We have to take this inside, so we will put this as P times u here and P times u, tau xx u and tau yx u. There is also another tau xx, yes, here u times tau xx. This is at the bottom phase, so that is x star, y, z star, and at the top phase again this is u times tau yx delta x delta z evaluated at y plus delta y. We notice that even though this is tau yx here, this is acting on the bottom phase and the top phase, we still multiply with the u component because it is a force stress which is acting in the x direction. So when we take the dot product like this, then we should take only the u vector, u component. And so finally we have the left back phase and the front phase. Back phase will give us minus tau zx times u times the area, which is delta x delta y, this whole thing evaluated at x star y star z, and the front face will give us tau zx u delta x delta y at x star y star z plus delta z. So these are all the rate of work done terms coming from the forces, stresses acting on in the x direction. You have 2 pressure components and 6 stress components, each of which is multiplied by u here. The stress times the corresponding area which is changing, and all of them multiplied by the same velocity component coming from the velocity here for the rate of work done. And we can similarly write down the 6 stress components and 2 pressure components acting on the y in the y direction, okay, and those 6 will add the corresponding energy terms, rate of work done terms, and there will be another 6 stresses and another 2 pressure forces acting in the z direction. So if you consider, for example, the pressure here and the pressure here, and there will be a tau yy which is acting in this direction and tau yy acting in this direction, okay. So we can write them down, and when we consider all the stresses acting in the y direction, we have to multiply by the v component of the velocity vector. So let us just do that. Minus p times the area which is delta x delta z times v evaluated, this is plus v at the bottom face x star y z star minus vp delta x delta z at x star y plus delta y z star. So these are the 2 pressures, and the stresses, if you consider the positive x phase, then that is tau xy times the area will be delta y delta z multiplied by v, and this whole thing is evaluated at x plus delta x y star z star, and the same thing on the negative x phase will be acting in the negative y direction. So that is minus tau xy delta y delta z times v at x y star z star. We can go a bit faster. Now tau yy times v at x star y plus delta y z star plus v minus v tau yy at x star y z star. This whole thing is multiplied by the corresponding area which is delta x delta z plus v times tau zx at x star y star z plus delta z minus v tau zy here zy evaluated at x star y star z, this whole thing multiplied by the area which is delta x delta y. So we have 1 2 3 4 5 6, all these things multiplied by the velocity component v. These are the rate of work done by the stresses acting in the y direction, and we will have 6 more terms coming from the z direction. We can write them down here, and all these 6 stresses and 2 pressures will be multiplied by the w component. So that is w times p at x star y star z plus delta z plus w times p at x star y star z. This whole thing multiplied by the area, which is delta x delta y, and the stresses in the on the x faces will be plus tau xz times w at x plus delta x y star z star minus tau xz w times x y star z star. This whole thing multiplied by the area, which is delta y delta z, on the two y faces plus tau yz times w at x star y plus delta y z star minus tau yz at w at x star y z star, both these multiplied by the corresponding area, which is delta x delta z, and the stresses on the front and back faces. So that is tau zz times w evaluated at x star y star z plus delta z minus tau zz w at x star y star z. This whole thing by times the corresponding area is delta x delta. So this is the overall expression for the energy equation. So we see that E plus internal energy plus kinetic energy being brought in and taken out by the flow, and the heat that is being brought in and taken out by the particular mechanism. Okay, this is the heat flux, and then the gravitational work done, source term here, and then the stresses. And as usual, we divide the whole equation by delta x delta y delta z and take the limit as delta x tends to 0, delta y tends to 0, and delta z tends to 0. And if we do that, then we can notice that from here this term here will become dou by dou t of rho E plus half rho V dot V equal to, now if we consider these two terms and then divide, we get divided by delta x, and when we take the limit, that becomes dou by dou x, and this becomes minus dou by dou x because this is coming at x plus dx with a minus sign. So and so we can write that as minus dou by dou x of rho u times E plus half and these two will give us similarly minus dou by dou y times rho V times E plus half, there is no here, and these two will give us rho W minus dou by dou z of rho W times E plus half V dot V. I think we have put an extra, yeah, it's okay. I think we have put an extra row in these things that should not be there. That is relatively straightforward for us to correct. Okay, so these are the flux terms, these are the energy fluxes being convected with the flow, and now we can consider these things. these two divided by delta x, delta y, delta z, and with the limit as delta x tends to give 0 will give us minus dou by dou x of qx minus dou by dou y of qy minus dou by dou z of qz, where qx, qy, qz are the fluxes in the xyz directions of heat, that is of the heat flux vector associated with the heat conduction. And we have this rho times st, that is the external source term, and when we consider these things plus rho u gx plus v gy plus w gz as the rate of work done by the external gravity vector, and the pressure here, this is pu at x minus pu at x plus delta x, so that becomes minus dou by dou x of pu, and similarly here it is Vp at y minus Vp at y plus delta y dividing by delta x, delta y, delta z, and taking the limit will give us minus dou by dou y of Pv and minus dou by dou z of Pw. Now let us consider the stresses. Here it is u tau xx x plus delta x minus u tau xx at x divided by delta x, that is what we will get. So that becomes plus dou by dou x of u tau xx, and similarly these two terms here, this is y plus delta y, there should be a plus sign here, that is acting in the positive x direction. So this is u tau x yx at y plus delta y and u tau yx at y with a minus sign. So that will give us plus dou by dou y with u tau yx, and similarly the z phases will give us plus dou by dou z of u tau zx. So contributions coming from the stresses acting in the x direction, and we can similarly write dou by dou x of v tau xy, that is stress acting on the y phase on the x on the in the y direction on the x phases, plus dou by dou y of v tau yy plus dou by dou z of v tau zy plus stresses acting in the z direction dou by dou x of w tau xz plus dou by dou y of w tau yz plus dou by dou z of w tau zz. Okay, so this is the overall equation, the energy equation, and as usual we can bring this to the left hand side, and then we can write this. So as of now we have not this statement is not complete because we have not specified what these heat fluxes are. We know what the stresses here are. We can say that tau ij for a Newtonian fluid is mu times dou ui by dou xj plus dou uj by dou xi plus lambda times dou uk by dou xk delta ij. Okay, so what remains for us is to specify q, and for this we can take the Fourier's law of heat conduction. So this q is equal to k gradient of temperature. Okay, therefore qx with a minus sign, where k is the thermal conductivity, So Qx is equal to minus k dou T by dou x, and Qy is minus k dou T by dou y, and Qz is minus k dou T by dou z. So we can substitute all these expressions into this, and we can come up with the overall energy equation which we can write like this. Where H is the enthalpy, this is specific enthalpy, and tau ij is given by this expression, and k is the thermal conductivity, and capital D by dt is a substantial derivative, and in this compact form we can derive this. And the same thing where this particular term is called the viscous dissipation term. So all the frictional forces that are arising, all the viscous stresses are actually contributing to this dissipation here through this. We can show that this is a positive quantity, and therefore that the whole thing is with a negative sign, it comes with a negative sign, so that this is a source term. So the viscous dissipation is actually a positive quantity, so that this, if the flow is taking place, then the viscous stress will actually increase the temperature. In most heat transfer cases, unless we are talking about highly viscous fluids, this particular term will not be significant, and you can come up with much simpler expression. And for cases with constant density, we can write this as simpler form. Where this is rho Cp times T will give us the enthalpy essentially, K is the thermal conductivity, and for constant, this is the viscous dissipation term. If we neglect this, we can write down a simple form of this, dou by dou T of rho Cpt plus dou by dou xj of uj rho Cpt equal to dou by dou x of k dou T by dou x Okay, we can make use of the index notation. Let me finish this. Dou by dou xj of k dou T by dou xt. And of course we have neglected, we have left out the source term. St is here, rho st. When there is no st, then it comes like this, and which we readily identify as the standard scalar transport equation, where the scalar is Cp times T. Okay. So then we have it falls into the scalar transport equation, and this k is the effective diffusivity of the scalar. So this is an extra equation which is coming into the overall set of equations that we have, which are the standard form that we are familiar with, which brings in only one new variable, which is the temperature or the enthalpy. And of course we have the properties of the fluid like specific heat is coming, the thermal conductivity is coming into this. So when we want to deal with energy equation, when we want to deal with non isothermal flows, then we have to solve an equation of this form, which is a standard scalar transport equation form, which introduces one extra variable and which also brings in one extra equation. Therefore, we are not disturbing the overall balance of equations versus variables. So in this way we can take care of all non-isothermal flows.